from what we talked about yesterday. So don't worry about remembering everything. But okay, so this is joint work with Renjan Duan, Phil Gressman, and postdoc at my university, Penn Zhu. And the different parts of this are joint work with different people. But and I'll explain that later. So today we're going to talk about so-called optimal time decay rates for collisional kinetic equations in the whole phase. So we're talking about convergence to equilibrium in R3 in the whole space, or R if you want. But normally we just work in R3 because that's the physical dimension. So this is the Boltzmann equation again. So we have dTf plus v dot grad xf is equal to q of ff. And x is now in R3, whereas last time x was in the tortoise. And v is in R3, and time is always positive. And last time our main focus was this collision operator, q, this red operator. And for the purposes of this talk, the collision operator q is not going to be as important as the transport operator, which I put in blue here, the v dot grad xf. So in the situation of the torus, for the purpose of convergence rates, the main operator in this equation is really the collision operator, but for the purposes of convergence rates in the whole space, the most important operator is really this spatial operator, and we'll see how that works later on. So again, F is probability density, or sometimes called an empirical measure. And v dot grad x is the free transport term, and the important thing to point out is that for x and R3, the free transport term dominates the convergence rates in the sense that the collision operator q predicts very, very fast convergence rates, and it has this H theorem that it satisfies, and the H theorem tells you that things converge very, very quickly to equilibrium. But this, in the whole space, this transport operator slows things down, and it's kind of like puts a speed limit on how fast you can converge to equilibrium. And so Q is again this collision operator, and this equation was derived by Boltzmann and Maxwell. Okay, so let's just review. So the collision operator is local in T and X, and it's defined in this way: Q of F of G is equal to the integral over dv star, the integral over d sigma in R3 and S and the sphere respectively. And you have this collision kernel, and then you have this difference of these functions in terms of their different velocities, and these pre and post collisional velocities v and v star and v prime and v prime star move around on a sphere. So v and v star are the velocities of a pair of particles before collision, and v prime and v prime star are the velocity of a pair of particles after the collision. We'll discuss the collision kernel in a second. Okay, so Boltzmann's H theorem is the following quantitative statement. It says that the negative of the time derivative of f log f integrated over dx and dv is positive. And this is a manifestation of the second law of thermodynamics. And this entropy is maximized by these Maxwellian equilibria, where rho, u, and t are the density, bulk velocity, and temperature of the gas. And so the entropy is increasing, and it's maximized by these equilibrium states. So you expect convergence to these equilibrium states. The problem with this statement is, again, that it cannot be justified rigorously in the sense that solutions to the Boltzmann equation are unknown to have enough regularity and integrability in order to perform the formal calculations that are required in order to verify that for solutions to the equation this quantity is in fact non-negative. There's another degeneracy here, is that when you integrate over the x variables in the whole space, and if you put a Maxwellian equilibria into here with constants rho, u, and t, then this function is independent of space, and when you integrate over the whole space, you get an infinity. But so this is a little bit of a statement that you have to think about very carefully what you mean. But nonetheless, we're not going to worry about that right now. We're just going to point out that this is what the Boltzmann equation predicts, and our goal is to prove convergence in R3 starting close to equilibrium. Our goal is to figure out what the optimal convergence rates are in this case. Okay, so here's a new slide that you didn't see last time, which is the H theorem in some sense fails at a local Maxwellian. So mu or rho u and t, where rho depends upon t and x, and u depends upon t and x, and t depends upon t and x, are not constants, then this Maxwellian set is a stationary solution to the H theorem in some sense. So the H theorem peters out and it stops working and it fails when you enter into a local Maxwellian. But local Maxwellians are not steady-state solutions to the equation, so you cannot expect convergence to a local Maxwellian. So in some sense, this H theorem is not working completely properly. It has some problems. It has some degeneracies. It has a big roadblock that you come across. It doesn't work all by itself. Okay, so with that point of view, a key tool to overcome this degeneracy in a bounded domain such as the tortoise for small data is the Poincare inequality, as you hear. So u minus u bar, where u bar is the average of u in L2, say, is bounded by the gradient of u. And for reasons that I don't want to explain, this is a great inequality, and it helps you to overcome this degeneracy in the tortoise, for example. It helps you quite a lot. And this is a key fact that allows you to prove convergence rates, as we did in the last lecture, without while keeping in mind this degeneracy. So the thing to point out is that the Poincare inequality fails miserably in R3. It's just not true. It's false. It's a wrong inequality. You can't hope to use it in the whole space. And so this way of looking at things, which makes your life easier, is in the torus is a way of looking at things that cannot be generalized to the whole space. And so what you do instead is to employ this very, very old idea that's present in a lot of work, which is to seek out additional dissipative mechanisms for the components of the local Maxwellian. So I think at this level of generality, this idea is present in many, many, many works. Famous old work on the Boltzmann equation from the very early results, even to very famous results from the present day, is that if you're working in the whole space and you have this degeneracy of having the H theorem fail as a result of being close to a local Maxwellian, then what you can do to overcome this difficulty is to analyze these components of rho, u, and t in terms of how the equation operates on them, and obtain new sets of equations which give you additional dissipative mechanisms for the Boltzmann equation that allows you to kickstart the H theorem in some sense. So these new dissipative components may jumpstart the H theorem when it gets trapped in a local Maxwellian. This is a philosophical way of looking at what we're doing. Okay. So for the rest of the talk, I'm going to try to explain to you three things. I'm going to try to explain to you large time decay rates for soft and hard potential non-cutoff Boltzmann equation, which was related to the talks from the previous lectures. And then I'm going to explain to you optimal large time behavior of the Wasser-Maxwell-Boltzmann system in the whole space briefly. So this will be maybe an introduction to Ranjan Dwan's talk that he's giving on Thursday on the similar topics. And then lastly, I'll talk about lifetime decay of the soft potential relativistic Boltzmann equation in R3, which is a joint work with K. Azul. This is generalizations of old results of people like Bob Glassy and Walter Strauss, who's in the audience, to the soft potential case of the relativistic Boltzmann equation. And the message that I want to send to you is that we will see unifying themes in all of these works and also very different methods. So somehow there's a method here that applies to all of these very different equations that maybe is useful to you as well, I don't know. But you can see that there's some, even though these will be very different equations, there will be kinetic equations, and there will be sort of unifying ways of looking at things that allow you to find out what's going on. So I should say that chronologically these papers are not, this is not the chronological order of these papers. So the one in the middle is really the first in the chronological ordering of these papers, but it's not the first in terms of how I think is the right way to explain things to you. Okay, so again, we're going back to talking about the Boltzmann equation without angular cutoff. And so you have this collision operator, Q of Fg is equal to the same operator up here that we saw last time. And again, James Clerk Maxwell, whose statue is in your courtyard, figured out in 1866 that you can calculate this collision kernel precisely from a physical two-body scattering problem from an intermolecular repulsive potential like the one you see right here. And this calculation is done in many introductory physics textbooks that you see in college and graduate school now. But so once you plug in this repulsive potential, which describes the law with which two particles collide, then you can calculate exactly that the kernel takes a product form. So capital B is equal to the difference of B minus B star absolute value to the gamma times lowercase b of cosine theta, or cosine theta is this angle right here. And the angular singularity is again not locally integrable, so it blows up quite badly. It blows up like a power law of -1 minus 2s as theta goes to 0, where s is between 0 and 1. And so this operator at the top of the slide, the collision operator for the Boltzmann equation, is in fact the difference of two infinities, and you have to be very careful about how you define it and how you make sense of it in order to even have a well-defined operator. Okay, and the kinetic factor V minus V star to the gamma can be quite singular. It's in fact strictly bigger than -3. For our purposes, all we care about is that S is some number between 0 and 1, not including the endpoints, and gamma is any real number bigger than -3. Okay, so this is the non-cutoff Boltzmann collision operator. And we linearize again, so we take capital F to be equal to mu plus the square root of mu lowercase f, where mu is the global Maxwellian, 2 pi to the minus 3 over 2 e to the minus v squared over 2. And this is the global normalized steady state with normalized constants. And then the perturbation f evolves according to this equation. So if you plug this ansatz for capital F into the Boltzmann equation, you get dtf plus v diacritic center plus L of f is equal to gamma of f, where L is the linearized Boltzmann collision operator and gamma is the nonlinear collision operator, and they take these slightly complicated forms here. And in our context, Boltzmann's H theorem then says that capital F converges to mu as t goes to infinity, or lowercase f converges to 0. And so what we want to prove is that lowercase f converges to 0, and we want to figure out what the convergence rates are. So we have these results that we talked about last time, global distance of classical solutions to the non-cutoff Boltzmann equation for F0 small in the Sobolev space, and also rapid convergence to Maxwellian in T3. This is joint work with Phil Gressman. And So the point is that this result generalizes almost without modification to the whole space, given the existing technology in the field, which I won't discuss too much, that existed previously. But the convergence to equilibrium does not generalize at all, and that was a challenging open problem. And so that's what we are working on, at least for the case of soft potentials. And as I said last time, there's also these very nice works of this AMUXY team. Okay, so let me introduce some notation. So from the H theorem, the linear operator L is a non-negative function, and for every fixed t in x, its null space is given by the 5-dimensional space. N of L is the span of these 5 vectors, the square root of mu, v1, v2, v3, times the square root of mu, and v squared times the square root of mu. And so now these, we can define the orthogonal projection from L to R3 into the null space N of L by P, and then P of G takes the following form. So P of G takes the form A of G plus B of G plus C of G, where A of G then is a function like if you want A, B, and C to be orthogonal, then you have to be a little bit more careful than has been here. But this is just the idea that if all you care about is being the projection into the null space, then you can define A of G, B of G, and C of G just to be the L2 inner product in V with these basis functions. Okay, and now note that L of G is equal to 0 if and only if G is equal to P of G. And these are the linearized versions of the local Maxwellians. Okay, and now we further define a unified weight function. W of V is equal to the bracket V if gamma plus 2s is bigger than 0, and W of V is equal to bracket V to this funny power minus gamma minus 2s if gamma plus 2s is negative. And the funny power is just there for the sake of convenience. But both of these weights go to infinity as V goes to infinity, because in the second case, gamma plus 2s is negative. So you have a negative sign there, but that just makes everything positive in fact. Okay. And now again, we have these spatial and velocity derivatives. So partial alpha, partial beta is equal to alpha and beta are multi-indices. And so you have partial alpha 1 x1, partial alpha 2 x2, partial alpha 3 x3, and similarly for the v variables. So that just means you have alpha 1 x1 derivatives and alpha 2 x2 derivatives, etc. Okay, so this is our notation. And now, okay, so I want to talk a little bit about some previous stuff. So so it's been an open problem to determine optimal convergence rates in the whole space for the soft potential Boltzmann equation. That is when gamma plus 2s is negative with or without angular cutoff. So we've been talking about this angular cutoff assumption. We've been talking about how there's a lot of previous work that made this angular cutoff assumption. Now we're trying to work that does not make this angular cutoff assumption, because you actually get stronger results without making it, even if you have to work a little bit harder. But we're saying now that if gamma plus 2s is negative, then there has been, it's been a difficult open problem to prove optimal convergence rates in the whole space. And so there's basically 2 results that I'm familiar with. So there's this very nice old result of Yukai Asano. And so normally in mathematics things are alphabetical, but that's the way the names are ordered on the paper, so that's the way I write them on my slide. And so with angular cutoff, so if S is equal to 0 here, so if there is this cutoff of the angular singularity, then Yukai Asano proved these decay rates that I'm going to call optimal. So if gamma is strictly bigger than -1 and less than or equal to 0, so notice that means that so gamma could go down to -3. So this only includes between -1 and 0, but nonetheless they can prove these optimal decay rates. So in the L infinity norm and the HM norm for certain values of m, where m is just the index of derivatives in the Sobolev space HM, then if you have this bracket V, B, F, it decays like 1 plus t to the A, where A is this funny number here. A is actually it's not that funny of a number, but it's n over 2 times 1 over p minus a half, and that's the main part, and then that's the min of that with 1. So this says that you get optimal decay rates in n-dimensional space for n bigger than 2 if n is 1, 2, 3, 4, and maybe 5, and if n is 6 or bigger, then you get a decay rate of 1, which is not necessarily optimal. But and the assumptions are that this quantity right here is sufficiently small. So for p between 1 and 2, then you have the initial condition times some weight in this L infinity HM norm plus F0 in this L2 LP norm is sufficiently small. And so this is really nice stuff, and it uses the spectral theory of the linearized operator, which seems to be a very, very hard way to look at things. And still, this is the best result using those kinds of methods to this date. Okay, so the next result that I want to talk about is these this AMUXY team. They proven results related to ours, and they prove optimal L2 decay rates for the hard potential case, gamma plus 2s is positive, and for the soft potential case in this range of parameters, gamma smaller than -2 and bigger than this quantity. So it's bigger than either the larger of these two, whether it's -3 or -2s, -3 over 2. This depends upon the value of s. If s is very small, then the first number is the larger one, and if s is very big, then the second number is the larger one. But then they prove this decay rate. So the supremum in the x variable times the hk norm, the hk minus 3 norm, is bounded by 1 plus t to minus 1, and then k is bigger than 6. Okay, and this so this is a really nice result, but this L infinity decay rate for the soft potentials is not optimal. So we wanted to see if we can prove the optimal decay rates. Okay, so this is what we are going to talk about now. So for certain technical reasons, we are working in n dimensions, where we're assuming that n is bigger than 3, because the n equal 2 case seemed to require additional work, and I was a little bit lazy. But so from previous work, the issue of determining optimal decay rates for the soft potentials was not clear. Some people told me that they thought that the actual issue of figuring out what the rate was even unclear. I don't know. I wasn't so sure about that myself. But so we suppose that, so I'm going to tell you what they are in a second. So we suppose that epsilon KL, which is this quantity, is sufficiently small, where alpha plus, so you sum over multi-indices alpha plus beta less than or equal to k, and you have this weight to this power L to the minus beta, and then you have partial alpha beta derivatives of F0 in L2 in X and L2 in V, and then you have F0 in L2 in V and say L1 in X. You suppose this quantity is sufficiently small, then you can prove these optimal decay rates. So you can prove that the Sobolev norm in L2 of the solution F exists for all time, and it decays like a minus n over 2 in n dimensions. So this is like minus 3 over 2 in 3 dimensions. And so you have to make assumptions on the weights Pn and Qn, which depend upon the dimension, but I won't pain you to know what all those assumptions are. And then you get this better decay rate for higher order derivatives. So if you sum over at least one spatial derivative, and you have this weight, or if you project onto the microscopic part of the solution, I minus P, then you decay faster. So you decay like minus n plus 2 over 2. And these are, and so this is interesting. This is new for the soft potential case when gamma plus 2s is negative. This was somehow unknown. And then using this sort of optimal Sobolev inequality that we first used in my paper with Ranjan and Duan, you can get optimal decay rates for the L2 LR norm for any R between 2 and infinity. So you can even get to L infinity in X, and you get these decay rates of minus n over 2 plus n over 2R. So if R is equal to infinity, that's just n over 2. And then you get this other decay rate down here for the microscopic part of the solution for I minus P of F in the LR norm for R between 2 and infinity. That's I'm not claiming that this is optimal, because I can prove faster linear decay for this thing than for the nonlinear term. But for some reason, but at least it's worthwhile to point it out, because it it's faster than the other decay rates. So you gain this extra power of decay here. So it's interesting to notice that this term, even at the nonlinear level, decays faster than this term. Okay. So, yes?
Why do you say that's optimal? Under what?
So you
what
are
does optimal mean?
You are anticipating my next slide.
Okay, go ahead.
Okay. So in theory, you shouldn't claim things are optimal unless you can prove a lower bound for the same thing in terms of the same quantity. And those lower bounds are very, very hard to obtain in kinetic theory. I know no examples where people have lower bounds for these kinds of decay rates. But nonetheless, there's a whole industry of people writing papers talking about optimal decay rates for kinetic equations, and I'll explain to you why that is. So these rates are widely considered by the experts to be optimal, although it seems to be very, very hard to prove lower bounds. And the first reason why you can say that these are optimal is because you can take as the definition of optimality that the nonlinear decay rates that you prove are the same as the linear decay rates that you obtain using very, very refined techniques of Fourier analysis. And you think that the decay rates that you can obtain from the linear equation are much easier to get the fast optimal decay rate. And if you can bootstrap that and get the same thing for the nonlinear equation, then you say, well, I probably obtained the optimal decay rate because I got the same thing for the nonlinear equation.
Are those rates determined formally by scaling?
Yes. Yes. And so a lot of people in their papers, they say, we define our notion of optimality to be that the nonlinear decay is as fast as the linear decay. And okay, so another argument for why these rates are optimal is you can say that these decay rates are optimal in comparison to the early works of Yukai and Kawashima and others starting in the 70s, studying time decay rates for the hard sphere Boltzmann equation in the whole space. And so you're getting the same decay rates that they got for these easier cases of the Boltzmann equation. And the last reason that I consider to be compelling about why these rates are optimal is that you can compare with the sharp decay rates for the heat kernel. And a lot of people believe in this principle that the heat kernel is more or less the best you can do in terms of diffusion. And so if you know that the decay rates for the heat kernel are optimal and you are obtaining decay rates that are consistent with what you get for the heat kernel, then your decay rates are probably optimal. You probably can't hope to do better than that. Okay, so this is the justification of the decay rates. Okay. So I want to explain to you a few ideas for proving linear optimal decay for the soft potential non-cutoff Boltzmann equation, but it also applies to the to other self-potential equations, as we'll see later on. So you can define the Fourier transform in X to be f hat of t, k, and v is equal to integral Rn of e to the minus 2 pi I x dot k, and you integrate against x, and you integrate over the f function, and you define x dot k to be just the normal dot product of the sum of the components between x and k. And so a key step to prove time decay rates is to obtain a differential inequality such as the one we have here. Now this is a instantaneous time frequency differential inequality. So you define some high order function E, L of t and k, which is going to be equivalent to the L2 norm in V of the Fourier transform in X of f evaluated at t and k times this weight function to the weight L. And then you have to define this, you have to figure out how to define this function so that you can prove an inequality like this, where one hat k squared is the minimum between 1 and k. And so then if you could, for some positive number lambda, you can prove that the time derivative of this time frequency functional plus lambda times this min between 1 and k squared times the L2 norm to the weight gamma plus 2s of the WL times f hat is less than or equal to 0. If you can prove this instantaneous time frequency differential inequality, then you're in good shape, I claim, at least for the moment. Although you're not really in good shape because this norm right here is weaker than this norm. So normally when you do these things for the hard potential Boltzmann equation, this norm is of the same order as this norm. So the E is of the same order as this norm, but with the L2 gamma plus 2s. But when gamma plus 2s is negative, this is false. And so without getting into too many details, I'll just tell you that this is, I didn't find it to be an intuitive thing to do to figure out how to define this function EL. And so what you have to do is, in fact, define it in two different ways for high frequencies and for low frequencies. And so for low frequencies, you define E0L to be the L2 norm of f hat plus kappa, where kappa is some small number times the weighted microscopic part of the time frequency of the solution. So you have to do WL, and you have to hit it with I minus P, and you have to take the L2 norm of f hat of that for the low frequencies. And then for the high frequencies, when k is bigger than 1, you have to take the L2 norm again, but then you have to multiply by kappa prime, where kappa prime is a different small number, and you have to multiply by WL times f hat in L2. And so you have to use these two small numbers, kappa and kappa prime, and then you have to match things up. And then this, when you add these two together, you obtain that it's equivalent to L2, and you can use the equation to prove that you have a differential inequality like this one. So I won't emphasize that too much. Okay, so now I want to explain to you how do you prove decay from this differential inequality. So suppose you have this differential inequality, what do you do with it? And the idea is, so you have this differential inequality, and crucially this holds pointwise for t bigger than 0, k in Rn, and L in R. And this is important that it holds for every L in R, so L can be some very, very negative number. And you can still prove this differential inequality. And so the point is that for these soft potentials, when gamma plus 2s is negative, then WL times f hat in this L2 norm to the gamma plus 2s is comparable to e to the L minus 1. So it's not comparable to e to the L. So you cannot use a standard Gronwall type argument to close your estimates and to prove decay. But so the differential, this differential inequality above is degenerate, and we'll see how you can overcome this. So it's degenerate, but the key point is that even though this differential inequality is degenerate, this is actually a family of differential inequalities. It holds for every L in R, and you can use interpolation. So you can say that, so while EL is not bounded above by WL to the F hat of L to the 1 plus 2S, you can interpolate between higher and lower norms, and you can say that EL is bounded by EL plus J, where J is some positive number, and EL minus 1, where L minus 1 is exactly the power that you need, but the price you pay for that is that you have to put different powers on these two norms. And so then EL minus 1 to this power J over J minus 1 is bounded by exactly the norm you want to the power 2J over J minus 1. And then you have this EL plus J term left over. And this EL plus J term is bounded. If you had to leave this just like this, depending on time, you'd be in big trouble. But fortunately, since you have this differential inequality at the top of the slide, you can bound this EL plus J by the initial data of EL plus J for linear solution. So the time-dependent thing is bounded by the initial thing that you have. And so this is a trick that's reminiscent of something that I did in my PhD thesis with Yanguo. Okay, so now once you use this interpolation trick, what you end up with is the time derivative of EL and TK plus 1 plus lambda times this factor in K, 1 min K squared, plus EL to the J plus 1 over J. So you take this 1 over J plus 1 and you multiply it on both sides, and for good measure you also take the power J, 1 over J to both sides, and you obtain that EL to the J plus 1 over J is the factor that you get here, but then you also have to compensate with this EL plus, with this norm, which is EL plus J at 0. And now you can prove from there, what you can prove is that EL TK is bounded by 1 plus T to the minus J. Okay, so just by manipulating this inequality, you can, by integrating against time for this inequality and moving all the terms around, you can obtain that ELTK, so this instantaneous norm, is bounded by it's decaying, sort of, except for it's not really decaying because you have this 1 min K squared norming here, so as K goes to 0, it's not decaying, but then you can use this Holder, this standard Holder and Hausdorff-Young argument that was, I think, already present in Kawashima's PhD thesis to get the decay rates that you want. So you integrate over the frequency variables, and you use the Holder's inequality and the Hausdorff-Young inequality, and you can go from here to get the decay rates that you want. Okay, so that's that.
How do you use J?
J is any positive number, so you can choose J.
Choose B1.
You can choose J, so J, you're paying for any J by putting an extra J weight on the initial data, but you can choose J to be 1, you can choose J to be 10, you can choose J to be 100, but you can't get 100 decay rates out of the Hausdorff-Young inequality argument. You can only get the decay rates that you get out of this K squared factor here. It's a similar kind of stuff to what you did with glacia for the relativistic Boltzmann equation. In that one respect. Okay, so this is the idea that I wanted to explain to you for proving these convergence rates. And now I want to explain to you a little bit about this Maxwell-Boltzmann system. So you have two species of particles here, and you have two equations, one for ions and one for electrons. The F plus equation is the equation for ions, and the F minus equation is the equation for electrons. And I just want to give you a brief introduction to how this works, since I recently found out that Ranjan Dwan is going to talk about this on Thursday. But okay, so you have this equation, and you have global existence for this equation in the torus, which was initially done by Yang Guo, and then I myself did the whole space case a few years later. And we want to talk about the optimal convergence rates in the whole space, where again the concept of optimality is defined in comparison to other works. And so you have these two equations where Q is the collision operator, and they are coupled via the Maxwell system. So you have these electromagnetic effects coming into the equation for the electric field E and for the magnetic field B. And so dTE plus minus grad x cross B is equal to the integral of V times F plus minus F minus TB. And then you have the equation for B, and then you have the dot products of E and B satisfy these equations here with the gradient. And the initial data has to satisfy these compatibility conditions. So if you want these conditions to hold for all time, they better hold initially. And so you assume that. And I want to point out that what we did applies with, we're writing this for simplicity without any physical constants, because otherwise it would get even more complicated. But what we did actually applies to the case where you have unequal masses and things like that. Okay, so you perturb F plus and F minus in the same way we did before. You take mu plus the square root of mu F plus minus, and then the H theorem says that F plus minus converges to mu, or lowercase f plus minus converges to 0, and E converges to 0, and B converges to 0 in the whole space. And you have these local Maxwellians, which are P plus minus of G. And now you have A, B, and C here as local functions of T and X, but for each equation, the plus or the minus equation, you have a different A term. So you denote by A plus minus. And you consider vectors F equal to F plus F minus, and P is equal to P plus P minus for each of the ions and electron terms. And we consider linearized collision operators. L is equal to L plus and L minus, and gamma is equal to gamma plus and gamma minus. And without belaboring you with these definitions, again, they're the same as in the previous case, except for that now we're considering the hard sphere Boltzmann collision operator. Okay, so I want to sort of just give you one brief picture of what we have to do without telling you too much precise details. So we want to, if you remember what we said, maybe what I said maybe half an hour ago, you want to find that the H theorem is not enough, and you need to find sort of additional dissipative mechanisms from the dynamics of these local Maxwellian terms. And so what we do, one of the key things we do is to derive sort of balance laws for the Maxwell-Boltzmann system. And so you get these system of equations for the time derivative of A plus minus, the time derivative of B, and the time derivative of C. And you obtain these, well, I won't pain you with reading them to you. You obtain these by averaging against polynomials in the V variables multiplied by Maxwellians. And you have to be sort of really careful about how you get these things and how you analyze them. So the problem is that these equations are not closed. these equations are not enough. So what you have to do is you have to study these high order moment equations. And so you have to define these high order moments, theta ij, to be this L2 inner product of your function u with this quantity vi vj minus 1 squared of mu, and you have to define lambda ij to be equal to the L2 inner product of the u with this function v squared minus 5 vi mu to the 1/2. And then you can also derive equations for these for the microscopic part of these high order moment functions, and you obtain these functions here that I again won't read to you. But the point is, so L and G plus, L plus minus and G plus minus are functions of the linearized and nonlinear parts of the collision operator, and the point is that you obtain all these sort of sub-equations, and you are able to use them to somehow jumpstart the H theorem and to prove differential inequalities, which allow you to get the results that you want. Okay. So after a detailed analysis of the previous equations that I wrote down for you, you can prove the following differential inequality. So let f plus minus e and b be the solution to the linear Cauchy problem for the Boltzmann Equation, and then you can define some time frequency functional, which I'll call an e of t and x, such that e of t and x is equivalent to the L2 norm in v of the Fourier transform of f times the pointwise absolute value of the Fourier transform of e and the pointwise absolute value of the Fourier transform of b squared. And then you obtain this differential inequality. So for any t bigger than 0, k in R3, you have this pointwise differential inequality where this time derivative of e plus lambda k squared over 1 plus k squared squared times e again is less than or equal to 0. Now this is also degenerate. So when we first saw this inequality, I think we thought it was terrible because the dissipative term goes to 0 as k goes to infinity. So you have an extra squared term in the denominator, which says that this term is somehow degenerate. But this indicates regularity loss, and it's a feature of the Vlasov-Maxwell-Boltzmann system that there is regularity loss present in the system because of the hyperbolic nature of Maxwell's equations. And so this is, we think, sort of the best, or this type of regularity loss inequality is maybe the best you can hope for, and so you have to sort of work harder to prove the decay rates. But this is a key step, is to prove this differential inequality, and then to figure out how to use it to obtain decay rates for E based upon losing regularity. So you put more regularity on the initial data, then you actually can prove decays. Okay, so you define these spaces, and so this space E and M has m weights and all of the derivatives in all variables, and this space EH and M has m velocity weights, and it has, but it does not contain the first derivatives in the spatial variables for the components of F, but it does contain the zeroth order derivative of E, and it does contain the zeroth order derivatives of the microscopic part. And we do use the time derivatives in our method for simplicity, but you probably don't have to do that. Okay, and now we have a theorem which says that if you assume that this quantity EJM, epsilon JM, is sufficiently small, where epsilon JM is EJM from the previous slide at time 0 plus the L2 and V intersect the L1 norm of F0 and also the L1 norm in the spatial variables of E0 and B0, then let F, E, and B be the solution to the Cauchy problem for the Vlasov-Maxwell-Boltzmann system for nearby equilibrium initial data obtained previously, and then for any fixed M being 0, 1, or 2, some integer, then if this epsilon is sufficiently small for n plus 2 and M max 1, then you obtain the decay rate of minus 3/2 for the for this high order norm. And if additionally the n plus 5 norm is sufficiently small, then you obtain the decay rate of minus 5/2 for the high order. Well, this is 3D. Yes, this is all. This is in 3D. So the previous result was in ND. So I put an n here and an n plus 2 here. But they're consistent in 3D. We only worked on this in 3D because 3D is the physical dimension. Okay, so let me. So then you can also, let me just give you this slide very quickly. I won't read it to you completely because Renjo, maybe we'll talk about it on Thursday, and I'm running out of time. But so you have faster decay rates for different components of the solution based upon these optimal Sobolev inequalities. So the L2 LR norm and the magnetic part in the LR norm decays like that, and then the microscopic part and the electric fields and this other component decays a little bit faster. And you can prove these using optimal Sobolev inequalities. So I want to, since Walter is here, I want to explain something else that I did. I might have skipped this if Walter wasn't sitting here, but since he worked quite a lot on this, I want to explain this thing that we did very recently. So for the relativistic Boltzmann equation with the soft potentials, then we also tried to prove some kind of an optimal convergence result. So this is the relativistic Boltzmann equation. And the difference here is that we replace V with P over P0, and you replace the collision operator C with collision operator Q from the previous one with C, and then you have this operator C, and you have these very nice old results by Glassi and Strauss proving global existence and convergence rates both in the torus case and in the whole space race, with the convergence rates in the whole space being optimal in comparison to the stuff that I've just been talking about for the case of hard potentials. So where sigma satisfies some sort of a hard potential assumption, but there's also a soft potential assumption in the literature that I won't make you understand carefully right now. But we consider the soft potential case to be important because when you want to use a relativistic Boltzmann equation, particles are expected to be moving very fast, and under those situations you think that the soft potential collision kernel might be important. And so we prove these, and so that you have all these definitions, which I won't try to read to you, but you can, so we have this theorem. This is my last slide. So we can prove with Keaju, who's a postdoc at the University of Pennsylvania, where I work, we can prove that you have these rapid convergence rates in the whole space that are believed to be optimal in comparison to the previous stuff. So for the soft potential relativistic Boltzmann equation, if F0 is in L2 in momentum space intersect LR and the spatial variables, and then it's in L infinity in the momentum space intersect L2 intersect L infinity in the spatial variables, and if the initial data is sufficiently small with some velocity weight, then you can prove that there exists a unique global mild solution to the soft potential relativistic Boltzmann equation, and the solution converges rapidly to equilibrium. So the L infinity norm times the L2 norm intersect the L infinity norm decays like 1 plus t to the minus k, where k is any number bigger than a half and less than or equal to sigma r0, where sigma r0 is this optimal linear convergence rate of 3/2 times 1/r minus 1/2. Okay, but you have to pay with extra weights in order to gain extra convergence on the solution, and the solutions can be shown to be continuous if they're continuous initially, and you have positivity if you have it initially, and thought this was a really nice result. And K worked very hard on it, so I was impressed. Okay, thank you. If you want to follow any of this stuff up, here are a lot of the papers that I talked about today and yesterday. And, well, I guess I didn't talk about this first one so much, but that was the first paper that I wrote with Rajan Dwan. And then, okay.